Hi, welcome to today's video lecture. We're going to be continuing exploring Collimator. So Collimator is a software, it's totally web-based. However, it's sort of Python's answer to Simulink. So just like in Simulink, you can build very complex models, but it's makes it very easy to do. There's a nice graphic user interface with a lot of pre-built blocks like controllers or transfer functions or inputs, outputs, or integrators. Specifically today we're going to be talking about developing a model for a gravity-drained tank. So I'm going to talk just briefly about the physics of building such a model. So if we look at a tank here, we want to keep track of the volume in this tank as well as the height. So the height multiplied by the cross-sectional area of the tank is going to give us the volume. So that'll be a variable that we track. We're going to have inflow coming in here of Q in, and then we're going to have outflow of Q out. In the previous video lecture, we talked about assuming that there is a valve on both of these that we could control directly. Now we're going to be making the assumption that we can only control Q in directly, the flow in, and we're going to assume that Q out is a function of the tank height. So as you build up height in this tank, you have more and more liquid just pushing this out. So the Q out is going to be a function of tank height. So specifically, we're going to use a common relationship where we have Q out is equal to some constant. Let's just call this C valve multiplied by the square root of the tank height. And basically what this means physically is that the higher the level of liquid in this tank gets, the more you have gravity pushing flow out. So as this gets higher, our outflow will get higher. If we wanted to write a balance equation, assuming that the density of the fluid stays constant throughout, then we can do a volume balance, which would be equivalent to a mass balance for the system. And that would just be that dV dt is equal to Q in minus Q out. And we could also make the substitution here using that relationship for Q out and get that. Oh, sorry. And get that dV dt is equal to Q in minus our C valve times the square root of height. We would also have an intermediate relationship. Here notice that we're using dV dt as our differential variable, which means that V is our state variable, our dynamic state variable. However, H is going to be a function of volume, and we're going to do this by saying that the volume is equal to the height multiplied by the cross-sectional area of the tank. And then rearranging that relationship, we would get that H is equal to V over A. All right, so I've defined some parameters for this model, which I'll just show on the screen briefly. So we're going to assume that Q in and Q out can both vary from 0 to 10 cubic meters per minute. Our tank volume, we'd expect it to be measured in cubic meters, and these limits aren't particularly meaningful now until we're doing some control things, but these are the ranges on our volume and our tank height. Some of the parameters that we will be using, we're going to use a tank diameter of 4 meters, and this reactor valve constant, or this C valve, we're going to use 3.2, and then it has units that just match up so that our units all cancel out appropriately. All right, so now we're going to take this mathematical model that we just developed, and we're going to translate that into Collimator, and I'm going to show you how to simulate a system like this. So our first step is going to be to open up Collimator by going to collimator.ai. You can go to try for free. So that's going to bring you, if you've already logged in like I have, it'll bring you to this projects page. So a project allows you to add a bunch of different models to our system. So I'm going to dive into lecture 2, which was from the last video, and just remind you of what we developed last time. So we had a model with two inputs, Q in and Q out, And then we had this simple Python script here, and our model was simple, just dvdt equals qin minus qout. Um, and then we took dvdt and integrated that with this integrator, which we gave an initial condition of 10 cubic meters. So we could simulate this system really easily. The difference now is that we're no longer going to define qout as something we can control directly, but rather we're going to set it up so that qout is a function of one of our state variables, which is v and ultimately the tank height. So I'm going to go back to my main screen by clicking on this button. I'm going to go back to my project screen. I'm going to start afresh here for the sake of walking all my viewers through how to do this again. It takes repetition to be able to master a software like this. So I'm going to start out with my core simulation block that's going to have my volume balance, and I want that to be a customizable Python script. So I just search for Python, I drag and drop a Python script onto here. When I double click, it gives me this really simple base code to kind of help me get started, saying out equals in. I would rather customize the names of my inputs, so I'm going to come over to this pane on the right. I'm going to have an input called qin. I will have another input later on, but I'll get to that later. If you remember, we do not want qout to be a directly controllable function. Rather, qout is going to be a function of our tank height and tank volume. So I'm going to have a similar output as last time. So my volume balance ultimately is going to help me calculate the derivative of volume with respect to time, or dv/dt. So I will define that as an output. I want to add more outputs here. And specifically this time I'm going to set up qout to be an output. It's going to be something that we calculate within our code. And then if I want to be able to extract that information into Collimator and plot the data or export the data for analysis, I want to have qout be an output. All right, another output that we're going to want to calculate in this model is going to be h, or our tank height. And then another thing that I like to do for model readability is I like to change this block name so it's a little more descriptive. So I'm just going to change that to be tank. Okay, so back into this Python code section, there are three different sections here. There's the step, where it says step. This is the code that will execute at every step in time as your collimator model advances through your simulation. This init section, this is code where you need to predefine things that need to happen at the beginning of your simulation, but this doesn't need to happen at every step. So this will help us to initialize our model. And then finally, you can do some post-processing steps in this block. We're not going to use this finalize section, but however, this time we are going to use the initialization section. I'm going to be doing some ever so slightly complex mathematical calculations, and I'm going to import the NumPy from Python. So I would put that code here. And NumPy is just a Python package that allows us to do some still fairly basic calculations, mathematical calculations. So I'm going to import NumPy as NP. So when I load my model, this will run at the beginning, allowing me to have access to NumPy as I go and step through my code. I'm going to go ahead and delete this block, and here is where I'm going to start coding in my basic model. So I'm going to start with this core material balance, which is a differential equation, and this is qin minus qout. So dv/dt equals qin minus qout. However, remember, qout is not something that's going to be directly defined. It's something that we're going to have to calculate. So I'm going to work backwards here a little bit. And here is where I'm going to say qout is equal to C valve. This is the constant that tells us how fast the tank drains as a function of height. So this a bigger C valve constant means that my tank is going to drain faster relative to height. And so if you remember, that relationship was C valve times the square root of height. And here is where I'm going to use NumPy, a NumPy function. And that's where I'm going to put this height. All right, if you are paying close attention, you've noticed we've never defined C valve. We did not include it as an input. So we could certainly come over here and make C valve an input. C valve is a constant. It's not something that we're going to want to change during the simulation. So my preference would be rather to define C valve as a parameter here. So when I'm in this specific Python script block, this allows me to define parameters that are specific to this function block. And so that value of cvalve was 3.2. The other parameter that we needed is the tank diameter, and that tank diameter was 4 meters. So now I've got these two parameters. They're just defined. They're just going to stay a constant throughout my whole simulation. Unlike my input qin, which is something that we can change. We can make it a step function or a sine wave or a pulse or a ramping function, or we could bring in data from a spreadsheet to have it feed in that input. We do not want to do that with our parameters. I like to use these spaces to define things that are constant, and we just want them to stay the same. And we don't want to create this extra noise in our model or extra busyness in our model. Okay, so working backwards through our code, we've defined what qout is. We also need to define tank height. So if you remember, our tank height is equal to our volume over our cross-sectional area. So I'm going to go ahead and say that our height is equal to our tank volume divided by the cross-sectional area, which is going to be np.pi. This is just pi 3.14. And then we need to multiply this by our tank diameter squared over 4. All right, so now if we know what the volume of our tank is at any point in time, we can calculate the height. Once we know the height, we can calculate the outflow. Once we know the outflow, we can calculate the rate of change of our volume. There's one other piece here that is still missing, and actually this function will not be able to compute because it still doesn't know what the volume is. So here is a little trick that I use using this collimator tool, and I actually take my differential state variable and I put this in here as an input. So our model, in order to function properly, is going to expect both the inflow and the current tank volume as inputs. If I click back out, you'll notice that Collimator has automatically created these ports. If I make this a little bigger and right click, I can go to toggle port labels, and that gives me all the variable names here. So we're going to now work at connecting this thing. All right, so one thing I'm going to do, remember we wrote the code so that given all of these inputs, it could calculate the change in volume with time. So if we integrate the change in volume with time over time, then that will give us the volume. So I'm going to have an integrator block here. And I'm going to left click and connect this dvdt to this integrator block. I'm going to give this integrator block a name of volume because its output is going to be my tank volume. And I'm going to give this an initial condition of 0. So we're starting with an empty tank. Now, especially with this integrator populated with an initial state or an initial condition, now I can take the output of this integrator, which will be volume, and I can loop that back as an input to my model, because my model explicitly depends on volume in order to compute height and my outflow. So the model should be complete in that sense. Okay, so now I'm going to I need to define this input, so I could use a constant here and just define a constant inflow. I want to see something a little more interesting happen here, so rather I'm going to do a step function here. And so again, just for model readability, so as an engineer, I want to know what's physically going on in my model, and it takes away one step of having to interpret things if you just give these blocks names. So the output of this step function I'm going to call qin. So once I highlight this qin block, this lets me define some of the parameters associated with that block. So a step function requires a start value. So in this simulation, I'm going to start filling up this tank. I'm going to give it a flow rate of 5 cubic meters per minute. And what I want to simulate is that I fill up the tank, and then at some point I shut off the flow and I let the tank drain out. So I'm going to give this an end value. I'm just going to give it a small end value of 0.1. So we're not cutting off the flow entirely. We're turning it way down. And then I didn't really cover this, but I'm assuming that the time units of my model are in minutes. So at time t equals 30 minutes, is when I'm going to turn my flow down from 5 cubic meters per minute down to 0.1 cubic meters per minute. And again, here when we look at our initial state, we're going to start out with an empty tank, and we're going to gradually fill up that tank. So I do want to connect this input to the input port on my tank model. And I believe at this point we should be just about ready to go. However, I want to define more model level parameters. So I'm going to click on just part of the blank canvas here, and I'm going to look at some of the model level parameters, and specifically I want to change my simulation time. So I'm going to simulate this whole system for 60 minutes. Remember, I'll make a step change, cutting off the inlet flow about halfway through at t equals 30 minutes. I don't want to hit go quite yet. First, I want to tell Collimator the different things that I want to view. So I want, where I left click on these little graph blocks, that means I want Collimator to produce a graph of that particular block's output. All right, my simulation is now complete, so let's go and inspect the results. So this shows me my step function input where I'm decreasing the flow from 5 down to 0.1. It does show me all the outputs of my tank. So notice that this is done in a hierarchical way where it gives me my model dot variable name. So I have here's tank dot dvdt. So our volume is gradually increasing, so we have a positive dvdt. This levels off close to 0, indicating that we're close to steady state. However, when I turn off the inflow, suddenly my tank volume starts decreasing and that dvdt switches to negative. So this is all jiving and making physical sense. If we look at our outflow, I'll get to that one later. Let's look at our height and our volume first. Remember that tank height is just a simple algebraic function of volume. So these two kind of mirror each other. So as I start filling up the tank, it does reach this close to a steady state value, not quite. Then when I turn off that inflow, my tank height starts gradually dropping, and you can see it kind of asymptotically approaches this minimum height. All right, so this is great. One thing that I can do to help visualize things a little bit better, I want to add these two flow rates to the same plot. So I can left click and hold on this green area for this guy. I'm just going to move this up a little bit gradually. I don't know of a better way of doing this yet, but now once I've got the Q in plot and the Q out plot adjacent to each other, I can either look at these side by side by dragging this over to the right or to the left. So if I drag it to the left, that gives me these two side by side plots. I can actually put them on the same plot if I drag this guy over here and put it on the bigger shaded graph area. That'll create a single plot that shows Q in and Q out side by side. So we've just created another physics-based model. Another thing that's convenient in Collimator is even when I have the visualizer minimized, I can still come in here and hover over each individual signal and have a quick little preview of how that looks. All right, so stay tuned. For our next video, we're going to be adding more physics to our model. We're going to be adding a chemical reaction to this and having that chemical reaction solve simultaneously to our volume balance.